So coming into our next part, let's talk a little bit more about the dust. And one example of how we know about the dust being out there is you see these different bands of light coming off the Milky Way. And that's due to what we call zodiacal dust. So that's dust closer to Earth's atmosphere, scattering the light. So here's another diagram representation of the dust out there, right? And this stuff will range in sizes of, say, a couple molecules. So you're saying a few atoms stuck together, or a little bit bigger. You get upwards to 300 nanometers. So you're going to have a handful of atoms to a couple 100,000 atoms making a little bit of molecule. And most of the stuff is going to be some kind of rock. Could be silicate, could be graphite, just some kind of rock. And around that is going to be a little mantle. Definitely some sort of ice. It could be some type of water or methane or ammonia, something that is just frozen around that rocky core. So that's going to be our dust and the cosmos. Now, this dust is going to interact with light in a couple of ways. And so the first one, I want to use a rocking boat analogy. So in this analogy, you've got your boat and the waves, right? The waves are about the same size as the boat. Specifically, the wavelength is about the same size as the boat. So if the wave is the same size as the boat, what happens to the boat? It has a very rocky adventure, right? The boat will rock a lot because of these huge waves causing it to dip up and down. So if the wavelength is on the order about the size of the boat interacts a lot. So if I take my dust particle, if the wavelength of light is about the same size of the dust particle, then the dust will interact with that light. It'll vibrate a lot. Now, if I go for a long wavelength, then the boat has a simple ride. It's not a hard trip. And therefore, the molecule, the dust particle, if the wavelength is long, much longer than the size of the molecule, then it doesn't interact as much. And so the dust, right, what types of wavelengths of light can get through the dust depends on how big the dust is and the wavelength of light coming through. So definitely have this idea of the rocking boat analogy. The size of the dust, what light it blocks, is related to, or the wavelength of light that dust blocks is related to the size of that dust. So other things that can happen. You could have your interstellar dust particle, and you could have starlight traveling through the cosmos, right? And that dust is going to absorb some of it. And what happens? If I absorb some photons, say I go to the beach and try and get a nice little suntan, I'm absorbing photons, I warm up. If I'm hotter, if I'm a warmer object, then I need to give more thermal radiation to reach that equilibrium, right? I'm absorbing a bunch of energy, I must radiate it away at an equal rate. And so this dust is absorbing a bunch of photons and then starting to glow in the infrared spectrum. We're going to see examples of the consequence of this phenomena on our view of the cosmos in just a few slides. Similarly, now that dust could form inside a giant interstellar cloud. And so we've got background stars trying to radiate different types of photons at us. And as it penetrates the gas cloud, only certain wavelengths of light are really capable of getting through. So the clouds and dust, what they do is basically filter the light that can get to us. So when the dust absorbs light, it becomes thermal energy and glows. That is exactly correct. As the dust is absorbing this, let's go back a slide. Right? As this dust absorbs photons, it gets hotter, And now it's a hotter object, it will glow, and it has to be a thermal photon. Go back to section 5 for a brief recap of that. And so it absorbs this energy, and then it will glow in a bit more of an infrared spectrum. Thermal photons is the language that we like to use. And the same thing across the whole spectrum of the crowd. So what happens is that as we look across the cosmos, if there's gas and dust in our way, the stars are going to become a little bit fainter and a little bit redder. This is redder in the sense of shifting the wavelengths of light, but not the same thing as a Doppler shift. I have to distinguish between Doppler shifting and the reddening due to material blocking the light. So let's actually look at some pretty pictures, some actual examples of this in action. All right, here is a visible picture of the Milky Way, and we see the band of the Milky Way. There's definitely a concentration of light near the center of the Milky Way, and as you get further away, not as much stuff. We start to see more and more background stars, right? And this is our world. This is our view of the Milky Way and the visible spectrum, what our eyes can see. Let's shift the wavelengths. If we change what wavelength of light we see, we're going to change what layers of the cosmos we get to see. So here's the same picture of the Milky Way galaxy, but this is images pulled from what's called the Wide Field Infrared Survey Explorer, right? What it's doing is trying to capture wavelengths of light that are in the infrared spectrum, 3.4, 12 to 22 micrometers. So this is the below red. Our eyes can't see this, but we can build detectors to get these wavelengths of light. And we're seeing a lot more bands of material. We're seeing a lot more stuff out in the cosmos. If I go to even longer wavelengths, keep going, and our Milky Way galaxy, yes, we still see that clear defining line that is the Milky Way. But look at how filled the Milky Way is. And this comes back to what I mean about there's gas and dust out there. It's blocking a lot of the light in the visible spectrum. But that infrared, that long, these are wavelengths of almost a meter long. How do we get that picture? So radio telescopes. These are telescopes that are sensitive to wavelengths of light between micrometers to a meter. IRIS and COBE, I believe, are satellites measuring at those long wavelengths of light. And they scan across. Does far infrared mean long wave infrared? Yes, those are the same thing. So basically, as we're going across our electromagnetic spectrum, we're going longer and longer wavelengths. And that's what I mean by far infrared. We're going further and further into the red spectrum. So, the takeaway from this, yes, the Milky Way is just filled with tons of stuff. And when you look at it with the correct wavelength of light, you get to find more things in the cosmos.